Welcome to lesson 5-5 called Satellites and Weightlessness. Yeah, I realized that there's an H missing here. Sorry, guys. The objectives of this lesson are one, to be able to articulate how to calculate the speed of a satellite that's in orbit, and then also to describe why a person might feel weightless while in orbit. Let's talk about the satellite's motion. So, the question first to ask is what keeps a satellite in the sky? The answer, or at least the basic answer, is its tangential speed, its high speed. If a satellite in orbit stopped moving, or if some force caused it to slow down, it would indeed fall directly to Earth. And likewise, if not for Earth's gravitational pull, all that speed that the satellite is launched into orbit with would cause it to fly out into space. So, in reality, orbit is this delicate balance between the tangential speed of a satellite and the force due to gravity. And we're really trying to get those to balance in the right spot so we can have a nice, clean circular orbit. So the goal when launching a satellite is to place it perfectly into a state of uniform circular motion. That means that it basically is just relying on the centripetal gravitational pull of Earth to keep it in that motion. So we don't have to use any kind of fuel to increase that tangential velocity or decrease that tangential velocity to keep orbit. We want to get it in perfect circular orbit so that all of the force that's causing it to maintain its motion is coming from the Earth's gravitational pull, which is essentially endless, assuming that the mass of Earth stays the same. So here's the thing: if we want to calculate how much gravitational force a satellite might experience, because of the fact that it might not be that close to Earth's surface, like in fact the moon is quite far from the Earth's surface, we would have to use Newton's law of universal gravitation, which tells us the force of gravity between two objects at any distance. So it doesn't have to just be like on the surface of the Earth. It could be the gravitational pull that you experience from Earth at any distance from the center of Earth. And that law of universal gravitation is shown right here. It's capital G, which is a universal constant given in the previous lesson, but I'll go ahead and write it here. It's 6.67 times 10 to the negative 11. All right. It's that universal constant, big G, times the mass of the Earth, times the mass of whatever other object the Earth is attracting is. It could be a satellite. It could be the moon. It could be another celestial object. And this is all going to be divided by the square of the distance between that object and the center of Earth. Now, notice I said the center of Earth and not the distance from Earth, because those can kind of be two different things. Since the Earth has such a large radius, you might say that something has some distance from the surface of Earth, but that's not the same thing as the distance from the center of Earth. And R represents the radial distance between the two objects, between the object and the center of the Earth. Now, because we know how uniform circular motion works, we know that centripetal force that causes the uniform circular motion must be gravity. So we're going to set the expression that we know for centripetal force and uniform circular motion, and we're going to set it equal to the gravity that an object might experience based off of Newton's law of universal gravitation. All right, so just to be clear one more time, this is the gravity that an object might experience by Earth, and if it's in orbit, then this is the centripetal force that it must need in order to maintain uniform circular motion in orbit. All right. And this is actually very useful because we can cancel out the mass of the object and just worry about the mass of Earth and ultimately solve for V, which is the velocity that a satellite must have in order to maintain orbit. Okay. Understand that R is the sum of the Earth's radius and the satellite's height above the Earth's surface. In other words, it's the total distance between the center of the Earth and the object in question. Now let's discuss weightlessness. Now this is when you are in some kind of spaceship or space station that is in orbit around Earth. Why do we feel weightless? And it's worth talking about because the answer is not just because you're so far away from Earth that you don't feel as much gravity. In fact, the International Space Station is close enough to Earth where you feel a gravity that's not that far off from the gravity you feel on the surface of Earth. But you still feel weightless when you're on the ISS because the International Space Station is in orbit. And so I've kind of set up a little scenario here to help you understand why this is the case. So notice that we have some lady standing in an elevator here. And in the elevator, there is a scale that's attached to the ceiling of the elevator. And underneath the scale is attached a bag with some weight. Okay, it has some mass. And if we understand anything about kind of an object in a gravitational field like Earth's, we'll know that there is some force due to gravity pointing downward that is equal to the mass of the object times the acceleration due to gravity. And at the same time, there's going to be some normal force that's going to be in tension in this line that we'd call the weight of the object. And in a normal scenario, when you're just kind of sitting still or you're in some kind of an object that's stationary, then the weight of an object minus its force due to gravity should be zero. And in other words, the weight is the same as its force due to gravity. But in this terrible situation in which the elevator cable breaks, both the bag and the elevator itself begin to fall toward Earth with an acceleration that's equal to the acceleration due to gravity. In this case, as you can see here, the bag no longer exerts any downward force on the scale because the scale itself is falling in the same direction and with the same magnitude of acceleration as the bag itself. So the bag appears weightless, and the bag indeed feels weightless in this falling system. This is exactly why somebody in a Ferris wheel cabin might feel weightless if the centripetal acceleration on the top cabin downward is exactly 9.8 meters per second squared. Okay, so at that point, a person inside this top cabin might feel weightless if there's enough centripetal acceleration on that top cabin. And the same is true for a person on a spacecraft in orbit. You see that the ISS is orbiting Earth, and therefore it must have some centripetal acceleration that's equal to the acceleration due to gravity. So anytime you're in the space station, you are accelerating towards Earth with a gravity that you should feel, but because the space station is also falling towards Earth, it's not actually giving you any normal force, and therefore you don't feel any weight. You don't feel Newton's third law. You don't feel that opposite force pushing back on you because it's not coming from the ISS. You're just effectively falling with the ISS. That said, here are a couple of practice problems from the Giancoli text linked below. Good luck. I have a solution video for these 4 problems posted. See you in the next one, guys.